and welcome to another college math video. In this video, we'll continue working with probability. In particular, we'll be looking at the counting principle, which is how many different ways certain events can occur. So our objectives: look at vocab and concepts related to sample space and counting principle, and then solve applications involving the counting principle and tree diagrams. So our notes. So when we looked at the first section on probability, and even with odds, part of our goal was to figure out what the denominator would be, how many different ways a certain thing could occur. When the event was rolling a die, there's only 6 different ways, but as the events get more complicated, or if there's more than one event, it takes a little bit more thought on how many different ways it can occur. So the counting principle is helpful with that. So the counting principle is, if a first experiment can be performed in m distinct ways, and a second experiment can be performed in n distinct ways, those would each be numbers, then the 2 experiments in that order can be performed in m times n distinct ways. That's the counting principle to come up with how many different ways a thing could occur. Then we also have the sample space, which is a list of all possible outcomes of an experiment. We will see both of them dealt with in this first example. Okay, so our example. Sushi is a $14 million industry in Japan, and let's say there are 4 types of sushi at the restaurant you visit: Ikuri Gunkan, Sake Nijiri, Kappamaki, and Majuro Nijiri. I apologize if you know that my pronunciation is wrong. I do not eat much sushi. So we're going to find the sample space if we choose to eat 2 pieces of sushi with replacement. With replacement is a distinction we'll have to make in a lot of cases, with or without moving forward, because our answer will be different if the item is being replaced or not. So you can imagine these are the 4 pieces that are available, and you're going to pick one, and then they come back with the same plate of 4, and you pick again. With replacement means, again, all 4 would be available. So there's a couple things we're going to do. The first is the tree diagram. I'm going to call, for our purposes in the tree diagram, Ikuri Gunkan I, Sake Nijiri S, Kappamaki K, and Majuro Nijiri M. All right, so when we make our first selection, it's either going to be Ikuri Gunkan, Sake Nijiri, Kappamaki, or Majuro Nijiri. What we're building first is the tree diagram, which is one way to figure out what the sample space looks like. Okay, then let's say we had first chosen Ikuri Gunkan. That's our choice. The waiter leaves, comes back with the same plate of 4. How many different ways could our second choice occur? Not necessarily how many different ways. We know how many, but what are they? You could pick Ikuri Gunkan, you could pick Sake Nijiri, you could pick Kappamaki, or you could pick Majuro Nijiri. Okay, what if your first selection had been Sake Nijiri? Your second could again be any of the 4. Ikuri Gunkan, Sake Nijiri, Kappamaki, Majuro Nijiri. Okay, what if your first choice had been Kappamaki? Again, it could be any of the 4 as your second choice. Ikuri Gunkan, Sake Nijiri, Kappamaki, Majuro Nijiri. And again, this is because we have replacement. It would look a little different if there was no replacement, but we will talk about that. And then if your first choice had been Majuro Nijiri, you could second choose Ikuri Gunkan, Sake Nijiri, Kappamaki, or Majuro Nijiri. This is the tree diagram. This tells us a first choice, and then there's a second choice. And this is only 2 choices. Imagine if at this restaurant we were going to choose 3 pieces. The same 4 on the plate come out every single time, and we pick one. Off of each one of these letters, we would have to make the same branches with 4 coming off of it. These tree diagrams can get really big, which is why we have the counting principle. So we will get to counting principle. This is what the tree diagram looks like, and that is an option you have when coming up with this. So the sample space is the formal list of what our options were. The sample space looks like this. We could have picked first Ikuri Gunkan, then Ikuri Gunkan, or Ikuri Gunkan and then Sake Nijiri. Ikuri Gunkan, Kappamaki. It's the exact same information, just presented in more of a formal list format instead of the tree of here's first selection, then second selection, and then maybe third, fourth, whatever it might be. And so you can see what this list would look like. S, S, K. It's just first, second, first, second, first, second, each one. All the way down to Majuro Nigiri, Majuro Nigiri. Okay. Two different ways of approaching this. The tree diagram is a very visual way to look at it. The sample space is the formal list. But so the question does ask for the sample space. So we would want this whole formal list, just a few missing in the middle there. What's more often the case, or more often the question, is to ask what the sample space size is. And that's just how many different ways it could occur. So if I had asked, there are 4 pieces of sushi, you're going to choose 2 pieces with replacement. How many different ways can this occur? Maybe you can think of it quickly, maybe not, but you have to kind of imagine, all right, first I pick one, then I pick another. There's all these different ways that this could occur. The sample space size is counting up the sample space. So how many are there here? You can count through this list, or you can count here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16 different ways you could choose a first piece of sushi and then choose a second piece of sushi. Okay, this is if we count up the sample space or use the tree diagram. If we use the counting principle, to come up with the sample space size, remember, counting principle says if a first experiment can be performed in m ways and a second can be performed in n ways, then the sample space size is m times n. The 2 experiments can be performed in m times n distinct ways. So we have 2 events happening. There's a first piece of sushi being selected and then a second piece of sushi being selected. How many different ways can the first piece be selected? Well, there are 4 options. So 4. How many different ways can the second piece be selected? Again, there are 4. There is replacement here. That's why it needs to be specified. Sometimes it needs to be, sometimes not. If we were rolling a die, for example, just because we've rolled a 5 doesn't mean we couldn't roll a 5 on the next roll. So sometimes you'll have to keep in mind if it's possible or not. But here it would need to be specified. So counting principle says take each individual way that the experiments can be performed and multiply, and we get 16. The same thing, sample space size. All right, let's just answer one last question here. This example was with replacement. What if it was without replacement? The only thing that would change is if we had without replacement, is that a Kurogun-kan is the second choice. If a Kurogun-kan was first, that couldn't happen. Sake nijiri first, we couldn't have sake nijiri second. It's the plate coming out and there being 4 choices. You pick one, and then you pick again from the same plate, so it's not being replaced. So the only thing that would change is that each of these where the same thing happened is being cut out. So again, you could count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. You can count the sample space formally listed, or you could use the counting principle. The first piece of sushi, there are 4 to select from. And then for your second selection, you've taken 1 and it's no longer an option. There would only be 3. You would multiply using counting principle, and there would be 12 ways this could occur. Your sample space size. Sample space is the formal list. Sample space size is how many different ways it can occur. Let's actually do one more, because the formula for counting principle only mentions first experiment and a second experiment, but it could be that more than 2 experiments are happening. Let's say you're going to choose 3 pieces of sushi. We'll go back to the initial premise, which is with replacement. How many different ways to choose 3? The sample space size. Well, the first piece, you have 4 choices. The second piece, it's with replacement, so you again have 4 choices. And the third piece, again, replacement, you have 4 choices. 4 times 4 times 4. 64. Just one more selection causes it to blow up. I feel like I'm losing my mind, but I need to check it. Yes, it's 64. Okay, good. All right, so you just need to figure out how many different ways each individual experiment can be performed. I can't imagine a problem where you would be required to create the tree diagram. It's more of a starting point, but once you can see how the multiplication occurs, we just use counting principle because it's much easier to deal with. There are times when knowing what the sample space looks like is helpful. You just have to make that decision. All right. Let's see another example. At lunch in Greece, you choose a salad, choriatiki or horiatiki. Again, my pronunciations are probably off. A pie, tyropida, spanakopita, or zambontyropida. And a drink, tsipuro or tsikudia. Find the sample space size, the number of options you have for lunch. How many different selections are we making at lunch? We're choosing a salad. We're choosing a pie. And we're choosing a drink. Those are the 3 quote-unquote experiments. Remember, that's a really loose term here. The first experiment can be performed in how many ways? Choriatiki, horiatiki, 2 ways. The second experiment of pie can be performed in how many ways? 3 different ways. Tyropida, spanakopita, zambontyropida. And a drink, 2 different ways, tsipuro and tsikudia. So how many ways can our selection be made? 2 times 3, 6 times 2 is 12. There are 12 different ways you can order lunch if you're going to pick a salad, a drink, and a pie, all 3 of those. This question only asked for the sample space size, so we didn't necessarily need to list all the different options. We could, if you wanted to, make the tree diagram or use the initials of the different items to come up with what the sample space would look like. This wouldn't be too long of a list, but you can imagine as more choices and more options within each choice get larger, that the tree diagram and the sample space just blow up. All right, another example. Let's say we spin 2 dreidels, one at a time. Possibilities of each nun, gimel, hey, and shin. We remember those from the previous video. Find the sample space. The sample space is the formal list of the options. So our first, I'm going to do a tree diagram first. You don't have to do it this way. The first spin could give nun, gimel, hey, or shin. And then off of each one, the same thing could occur. Nun, gimel, hey, shin. Nun, gimel, hey, shin. Nun, gimel, hey, shin. Nun, gimel, hey, shin. This is tree diagram. The sample space would be the formal list. So nun, nun. Nun, gimel. Nun, hey, nun, shin. Nun, gimel. Oops. That one's in reverse. Gimel's first there. Gimel, nun, gimel, 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 hey, gimel, shin. Again, you don't need the tree diagram. This is your sample space, this list right here. Hey, nun, hey, gimel, hey, 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 shin, shin, nun. Oh, my list has to spin a little bit, I think. Gimel, I'll bring it up top. Hey, shin, shin. Okay, so there's the formal list of the sample space. It doesn't ask for this, but what's the sample space size? You can count them, or you can use counting principle. 4 times 4, or count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, so the first question after we have the sample space, find the probability of spinning a double. So, with a probability, spinning a double is the event. First, we need to know how many different ways this can occur. We know there's 2 being spun, and so when we have the sample space listed, the sample space size is your denominator. There are 16 different ways you could spin the 2 dreidels. Of those 16, how many meet our criteria of being a double? Well, then just count. Nun, nun, gimel, gimel, hey, hey, shin, shin. 4 out of the 16, which simplifies to 1 over 4. The probability of spinning a double is 1 in 4. Okay, find the probability of spinning a hey and shin. Again, there are 16 ways that these 2 spins can occur, How many meet the criteria of being Hei and Shin? I'll circle these. We have Hei, Shin. If Hei was first, Shin was second. And Shin first, Hei second. So 2 out of 16. Simplify. 1 out of 8. So big picture, what this is helpful for, what the counting principle is helpful for, is often knowing how many different ways the event can occur is helpful with your denominator. Sometimes there'll be questions just asking how many different ways can this thing occur, and you won't necessarily look for individual probabilities, but both are definitely possible. All right, a couple more examples. Let's say there are 3 birthday cards randomly chosen from 10 birthday cards. So you're going to the store. There's 10 to choose from. You have to get 3 for your friends that all have birthdays at the same time. And you're going to look for the number of possible outcomes. And we're going to distinguish with and without replacement. With replacement means there are 10 different cards, types of cards, but there's multiple of each card. So if you wanted to, if you felt like one card was good for more than one friend, you could buy the same card with replacement. Let's use counting principle, because you can imagine if we attempted to do the tree diagram here, your first selection, you're choosing randomly, you have 10 different choices. So card 1, 2, 3, 4, 5, 6, blah, blah, blah. Okay, second choice, you also have 10. So off of each one, you need 10. And then your third choice, off of each one, each 10 that you've built, another 10. It gets crazy, so you don't want to deal with the tree diagram, and most of the time you don't even want to deal with what the sample space looks like, just the sample space size. So you're choosing 3 birthday cards. How many different ways are there for you to choose a first card? 10, because there are 10 different cards. There is replacement, so 1 is chosen, but all 10 unique cards are still available. You've just picked one of them. There's another copy of it there. So on your second choice, you still have 10 choices. And the same thing on your third choice, you still have 10 choices. So the number of ways, if you're choosing 3 cards randomly from 10 cards, 10 times 10 times 10, whoa, not 10,000, 1,000, is 1,000. I got a little zero happy. 1,000 different ways this could occur. Okay, how about if there's no replacement? The experiment is the same. We're choosing 3 different cards, but now these are 10 unique cards that are, there are no copies of them. They're each one of a kind. So when you make your first selection, you have 10 choices, but now that card is gone and there's not another one to replace it. So on your second choice, you only have 9 choices. And then on your third choice, you only have 8 choices because 2 are gone at that point. So if there's no replacement, 10 times 9 times 8 for your sample space size, or the number of outcomes, is 720. Like I said, sometimes it'll be very clear in saying with or without replacement. If that's necessary, it'll be listed there. If it's not, like rolling a die, you know that every single time there's with replacement because the same number is possible. It's not like one happens and then it's gone. So just watch out for that. All right. And then let's go to some practice problems. So these practice problems revolve around the standard deck of cards. We're choosing 5 from the standard deck. Remember that the deck consists of 52 cards, 13 are hearts, 13 are diamonds, 13 clubs, 13 spades, and within each of those 13, ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king. Again, I will have to expect that you know what the standard deck of cards look like to be able to ask different probability questions. So within this realm, we are looking at only finding the number of possible outcomes. Again, in 2 scenarios, with and without replacement. So go ahead, pause the video, see if you can go through these on your own, and we'll take a look in just a second. Okay, so let's see how many ways there are for this to occur. So we're choosing 5 cards. That means, according to the counting principle, there are 5 experiments. So we're going to find how many different ways each one can occur and then multiply them together. In the first scenario, the whole deck exists. We're picking one randomly. We're choosing a first, a second, a third, a fourth, and then a 5th card. there are 52 ways we could select the first card. This scenario is with replacement, so the card goes back, shuffle, choose again. All 52 are still available. Third, card goes back, shuffle, pick again, 52, and the same thing happens as we continue on. Every time you have the entire deck to choose from. Put one back, pick again. So 52 times 52 times 52 times 52 times 52. You can put it in the calculator. I would not do that by hand. It looks like we have 380,204,032 different ways this can occur. You can see how these numbers blow up very quickly. And this is if you were choosing a card and then putting it back every time. If there was no replacement, so what would more be likely in a card game, you would pick 5 and you would keep them for whatever reason. Who knows what the game might be that you're playing. But the same thing is happening. You have 5 choices to make, and we want to know how many different ways each can occur. Your 4th selection and your 5th selection. So the first selection can still be made in 52 different ways, but now you're keeping that card. So then there's only 51 cards to choose from. You keep it. Then there's only 50 cards to choose from. You keep it. 49 cards, you keep. And then 48 cards to choose from. There are many card games that involve 5 cards coming out of the deck, and it would usually involve a little bit more selection along the way with other people, but let's just say you're picking 5 and then you have to do something with those 5. How many different ways can this occur? Again, type it in the calculator. You get 311,875,200 different ways that this can occur. That's so many different ways in the standard deck of cards. There's only 52 choices, but when you're adding in more than one experiment, quote unquote experiment, it just blows up how many different ways these things can occur. So to reiterate, this section we had counting principle and sample space. Sample space isn't something that we'll usually list. Sometimes it's helpful for you to list the entire thing, but you don't always have to do that. What's more helpful is to be able to figure out how many different ways a set of experiments can occur, and we can use the counting principle for that. Sometimes it'll help with the denominator, sometimes that'll just be the question. But long term, this will be something we definitely use. So keep that in mind as we continue on, and I will see you soon for another video.